in the near surface and what happens with dissolved organic carbon. This is this biological pump we refer to in these carbon cycles that has to do with the glace ages. And this pump is really only about 10 gigatons per year, and only a fraction of that is associated with the amount of carbon to sink, a fraction of which sinks deep enough really to go to be sequestered for centuries. And so if we're going to do this, then we also need to build a lot of pipes to move a lot of the water around so that we can get these degraded materials down to the ocean floor. And so this would be a massive global scale fertilization and piping problem in order to move these around. And at maximum, maybe some fraction on the order of a gigaton per year could be extracted from the atmosphere. And it's really hard to imagine accomplishing this. There was an initial flurry of activity in the United States to do this kind of processing, and it is now not taken very seriously. Here's another picture. I like this cartoon a lot because it lays on a simple diagram the costs and benefits of these various techniques. So on this axis here, you have the negative emissions, that is sequestering carbon out of the atmosphere. Here's the energy per year that's required to accomplish it versus the energy per year that's produced. It's a very nice paper on Nature Climate Change. It's worth looking at. And this particular color scale represents the land requirements. And then the size of these droplets represents the water requirements. So those of you, by the way, who went to my assessment talk that I gave to the combined community, I talked about the visual display of information as being a really important new tool for students. And then look at all the information that's available on this graph through the clever use of pictures. I like this very much. Here's BECCS, okay? You see the land requirements are pretty severe, but we produce a lot of energy, and we have a very significant impact on mitigating CO2. And this is why BECCS is so popular. Direct air capture, the land requirements are minimal, but the energy requirements are extreme. But we also have a very significant impact. The water requirements for direct air capture are not so great, but the water requirements for BECCS is pretty extreme. And so you can examine various technologies on graphs like this, and it allows you to sort of assess the status of the technology that you may be researching as part of your research activities. So let's summarize the same Nature Climate Change article with a series of bar graphs that shows us how to compare all these various technologies. So here I have a bar graph. This is the atmosphere. Here's carbon underground. Here's carbon in the land, carbon in the ocean. And fossil fuel energy, as we consume it right now, takes carbon out of the geology and adds it to the atmosphere. That's where we're at right now. So we want to ask about bioenergy. So bioenergy takes carbon from the land and it emits it into the atmosphere. That is, we just burn wood to make fuel. If we do CCS, like Professor Reimer has been talking about, we take carbon out of the ground, we generate energy, but we put carbon back in the ground. And so ideally it's net carbon neutral. Here's bioenergy plus the so-called BECCS. So let's follow this out. We take biomass from the land, never gets to the atmosphere, it's sequestered, and therefore we reduce, because the land took up carbon, we decrease the amount of CO2 in the atmosphere. Direct air capture, just take it out of the air and put it underground. Enhanced weathering, take it out of the air, put it underground. Afforestation, take it out of the atmosphere, put it in the land. Ocean fertilization, take it, put it into the ocean from the atmosphere. So these are the ways to sort of visualize how these work in terms of these models or bathtubs for carbon. And so now we have to look at all the requirements necessary to accomplish this. A lot of land, a lot of water. We need nutrients that are depleted in the case of growing things, or we need fertilizer in the case of growing algae. Albedo modifications actually are a benefit for BECCS. If you take a parking lot and replace it with a forest, It has net benefits for temperature change locally. There are costs. The energy requirements for all these are really quite extreme. So without renewable energy and cheap renewable energy, not many of them are feasible. We need considerable investment to both pilot them and deliver them. Those investments have to come from people who have money. And how do they get that money? It's unclear. We can't rely on Bill Gates to fund all this. And so as a matter of public policy, we have to decide where these investments are. There are a lot of social effects associated with these, in particular the engineering of the land and water around us, the security, energy security, and of course the security of the land around you. And when there's CO2, you have a farm and people are putting gigatons of CO2 underneath your farm. There's a security and sensitivity issue there, and of course a safety issue. So in summary, the negative emissions technologies will most likely be necessary if we're going to meet the Paris Agreement. Net carbon dioxide removal from the atmosphere involves land use changes. All of these technologies need to be evaluated in terms of their costs, in terms of weather, energy, land, and there might be unforeseen negative consequences. And the real goal of climate intervention, after all, is to reduce radiative forcing. That is, reduce the, this greenhouse effect for the planet Earth. So it is 4:27. So I either end now or I end in 10 or 15 minutes. 10 minutes. I love Professor Singh. Fine. I made a small mistake and closed a file that I should not have closed. So if you will give me just one moment, because I know this is coming from my 10 minutes. Okay, I deleted the file. So I'll just say a few words and then I want to go through the summary with you. So you'll get a little of your time back. I apologize. So what is it Reimer and his students do in the lab exactly with regard to carbon capture and sequestration? Because I have not included in any of these presentations work that's specific to the students and postdocs who work in my lab. And so I mentioned direct air capture. And we've talked about amines. So one of the things my group has been involved in is building porous materials in which we append amines inside the porous materials. And so what you have then is this really nice benefit of the carbamate chemistry that goes with absorption. That is, CO2 reacts with an NH2 group to form a carbamate, but you don't have the water. This happens in a porous medium. So I've been working with my students for 2 or 3 years now on designing these porous materials to do this. And we discovered something really quite surprising, which is rather than chemically tether an amine inside of one of these porous materials, we actually just add the amine to the material as a liquid. And the amine sticks to the walls of the pores. And when it sticks to the walls of the pores, it moves. It's fluxional, as we say in chemistry. That is, these amine groups are moving. And they move in a very strange way. They move in a way in which the enthalpic forces, that is the energy it costs to move, and the entropic forces, that is the number of configurations available to the molecules that move, are in a delicate balance. And there's a place in the world where that delicate balance also occurs, and that's in enzyme chemistry, where you're placing an active site in a pocket that's dynamic. So we were surprised. It was completely accidental, I should say. We were surprised that when we did an adsorption isotherm on these porous materials with the amines aligned in them, that the isotherm was a perfect step function. That is to say, none was absorbed, and then whoop, it all absorbed at once. It wasn't Langmuirian at all, which grows slowly and rises. And it wasn't one of these type 2 or type 3 or whatever. It was a step function. It's really very rare in adsorption science. And we had a difficult time figuring out what it was. And 28 authors later in a paper in Nature, we figured out that what's happening is that there's a chain reaction occurring. The first CO2 molecule comes in, and it sort of weakens this dynamic process, which allows all the others to react instantly. And so that was the first exciting part, was to figure out this chemistry and the role of the delicate balance of entropy and enthalpy in this motion, so that we got these step functions. Why are step functions important? Because if you're going to desorb and adsorb, so imagine this is a temperature scale here, and you have this adsorption isotherm. At this temperature, it's all absorbed. At this temperature, it's none. And that delta T is like 10 degrees C for these materials. So that means temperature swing adsorption doesn't have to heat the bed very much to get the CO2 off and on again. So that was really exciting to us. And then we recognized, of course, that where does the step function occur in temperature? So you can tune the structure of the porous material, and you can tune the type of amines, and you can move that step function up and down in temperature. So we were able to craft the material so that it was optimal for doing desorption from a packed bed. So those of you that know engineering know about desorption from packed beds. You have to have heat transfer and so forth. So we were able to get the whole desorption process to occur below 100 degrees C. So water, doesn't matter whether water was there or not. So the effect of water went away. And then in the same studies, we recognized, can we tune that step function so that it's at 400 ppm? And you know why 400 ppm is important. That's the concentration of CO2 in the air. So I can run a temperature swing on a material where I capture CO2 at 400 ppm, change the temperature by 20 degrees, pull it off, go back and forth and back and forth. And so that's why Nature published the paper, is because we were able to knock sort of all these things off at the same time by really exploiting the kind of chemistry and physics that occurs in enzymatic systems. So we got lucky with that one, to be sure, but that's the kind of thing my research group does. And so sort of engineering and designing these porous materials for carbon capture. So let's call our attention then, in closing, to the summary of our course. Yeah?
Place for the adsorption?
So for direct air capture, you want absorption to occur at room temperature, 20 C, 30 C at the most, depending. And you want the desorption temperature to be less than 50 C. So you don't
After that,
need
it's like decreasing.
And that's it. You cycle between room temperature and 50 C, and the CO2 comes on and off and on and off. Really love it. So we started a company to deliver these materials. And somebody earlier on in the course was commenting about the cost, in terms of carbon cost, to make these organic materials. And it's not trivial, but then once you have a goal, then you can start engineering the reactors to produce the materials and drop the product. So the first time we did this, we were lucky to make 100 milligrams of this material to do the initial studies. But we're at the point now where we can produce 100 kilograms a day, so which is not enough to save the Earth. But it's certainly a big step forward from 1 gram, and that's just been in a matter of a few months. So what have we've looked at this in 3 parts. And first, I reviewed what I consider to be overwhelming scientific evidence that the atmosphere is changing, humans are the cause, and that there are consequences on virtually every level of the planet. In the second part, I introduced carbon capture as an effective scheme to mitigate the disposal of our waste in the atmosphere, and in particular examined 3 technologies for capturing carbon: adsorption, absorption, and membrane separations. And then finally, we looked at sort of the geology of carbon sequestration, the environmental risks, projects that are taking place to demonstrate that it can happen, and the various geoengineering schemes to decarbonize the atmosphere. So my conclusion for the students here is that the Earth needs your help to devise and implement schemes to decarbonize the atmosphere. And although there are many technical and policy challenges, the fundamental chemistry and physics and engineering of carbon capture and sequestration really pose no fundamental limitations on employing them to saving the planet. I want to thank you all for giving up a week of your time. Professor Singh is coming? Oh, yeah. So